There are three major forms of cytokine action: autocrine, paracrine, and endocrine. You may be more familiar with these terms from endocrinology when discussing hormones, but remember, cytokines are actually the hormones of the immune system. You'll come across this terminology referring to cytokines on a fairly regular basis, and much like endocrinology, these terms primarily refer to the distance between the cell secreting the cytokine and the cell receiving the cytokine. So let's start with autocrine. Now, we haven't talked much about T cells yet, as they are part of the adaptive immune response, and we're still over here in the innate immune response. But T cells give us our best examples of autocrine cytokine signaling. So let's dip our toes into the T cell world. Autocrine cytokine signaling means that the cell producing the cytokine also expresses the receptor that the cytokine needs and utilizes it, leading to changes in the actual cell. The prototypical example of autocrine signaling in T cells is IL-2 cytokine secretion and signaling. This also will enable us to talk about the IL-2 receptor, which is something you definitely need to know. Hint, hint. Interleukin-2, or IL-2, is the proliferation cytokine for lymphocytes. It makes one cell become two. It makes all lymphocytes divide, specifically NKs, Ts, and B cells. The IL-2 receptor is only on lymphocytes, making it so they can divide. Most cytokine receptors are made of multiple chains, and the IL-2 receptor is no different. The complete IL-2 receptor has an alpha, a beta, and a gamma chain. However, most of the time, not all three chains will be available to the cell. When a T cell has just completed its development, it is considered naive. This means it's kind of ready to go out into the world, and it can travel around the body, but it hasn't yet seen its antigen. I like to think of it kind of like a 16-year-old kid. In Illinois, you get your license to drive at 16, but you probably are still driving mom and dad's car, and you don't have a job, so you have no money to go and do anything, and you have a curfew. So you're free to go out and about in the world, but you really can't do much else. Well, naive T cells, as I said, they can travel around the body, and if they encounter their antigen of interest, they'll develop. But at first, they're just free to wander. Naive T cells express 2 out of the 3 chains that make up the IL-2 receptor. That is the IL-2 receptor beta chain and the IL-2 receptor gamma chain, which is also known as the common gamma chain receptor. And we'll talk about that more in a little bit. These 2 chains give the T cell a really low affinity for IL-2. So if there is IL-2 in the area, they won't really respond to it. It's a snack, but won't allow them to proliferate. Now, let's say our naive T cell grows up and sees its antigen of interest. At that point, it will express the high affinity IL-2 receptor alpha chain. This is also known as CD25. It's important to remember that, as that's a pretty important molecule for recognizing different types of T cells. So the high affinity alpha chain of the IL-2 receptor is CD25, and it is only expressed on T cells that have already seen their antigen of interest. This means these are T cells that are ready to carry out whatever their effector function is. So this will be induced. The alpha chain is induced. The beta and gamma chains are not induced. They are constitutively expressed on naive T cells and activated T cells alike. Now, when the high affinity IL-2 receptor alpha chain gets expressed, this, my friends, is much more than a snack. This is a Thanksgiving need to unbutton your jeans, tryptophan-inducing nap feast. So much so that the cell will divide. It will split. Now, not only will the cell begin to express its own IL-2, but it also will have the IL-2 receptor. So therefore, we get complete autocrine signaling, as I showed earlier, where now the T cell is making its own IL-2 and it is utilizing the IL-2 it makes. So that's an example of autocrine. It's kind of the quintessential version of cytokine signaling. Now, remember, I said the IL-2 receptor is made of 3 chains, alpha, beta, and gamma, and that the gamma chain in particular is called. The reason it's called the common gamma chain is because this particular chain is used with other alpha and beta and delta and epsilon even chains to form the receptor for several other cytokines, including IL-4, IL-7, IL-9, 15, and 21. This gamma chain is also the portion of the cytokine receptor that actually leads to changes in the cell. And that's because it has this intracellular cytoplasmic tail. This intracellular cytoplasmic tail acts as a scaffold to create signal transduction in the recipient cell. Basically, the gamma chain has this tail that leads to activation of the JAK-STAT pathway. The JAK-STATs are tyrosine kinases that transduce cytokine-mediated signals. These secondary messenger molecules will eventually lead to induction of transcription factors and transcription of new genes, like adhesion molecules, surface receptors, cell division, and in some cases, production of even more cytokines. Now, I mentioned that the gamma chain is shared with many cytokines besides IL-2, like IL-7. IL-7 is required for the development of lymphocytes. That's your T cells, B cells, and NK cells. If you have a defect in your common gamma chain, you have a big problem because you can make as much IL-7 as you want, but without an appropriate receptor, your body won't be able to recognize it. It won't be able to utilize the IL-7 you're making. So therefore, you won't respond to it. And when you don't respond to it, you don't make T, B, and NK cells. So there are patients who have these deficits, and it leads to a severe combined immunodeficiency. And we'll talk about that when we talk about primary immunodeficiencies. All right, let's move on to paracrine cytokine signaling. Paracrine is cell communication in which a cell produces a cytokine causing changes in nearby cells that possess the receptor. So this is short distance communication with a different cell than the one that originally made the cytokine. So again, let's think of T cells. You remember from your cell and terminology self-study that there are CD8 positive T cells that are responsible for killing things, and there are CD4 positive T cells which are helper cells because they secrete cytokines that help other cells do their jobs. Well, this is a great example of a paracrine response. So, for example, macrophages at the site of inflammation will gobble up pathogens, much as this macrophage here has. Now, they may be able to ingest the bacteria, but they might not have enough of the enzymes they use to kill bacteria localized to the area. So they need some sort of direction as to how to use these enzymes to kill this bacteria that they have engulfed. Well, enter the helper T cell. Now, this is an activated CD4 positive T cell. It's a Th1 cell, which is a subset of CD4 T cells that are really pro-inflammatory and help combat intracellular pathogens. This one has already seen its antigen previously. So when the macrophage presents the antigen to the T cell, it's basically saying, hey T cell, do you know what this is? Can you help me? And in this case, the T cell is going to say, yep, and it's actually going to produce the cytokine interferon gamma. In this way, it's basically delivering the cytokine to the macrophage it is attached to, which has the interferon gamma receptor. Interferon gamma was previously called macrophage activating factor because it literally activates macrophages, making them better at killing the pathogens that they have already engulfed. So then these enzymes can come in and kill the bacteria it has engulfed. There's also a concept known as mutual activation. Mutual activation occurs when one cell produces a cytokine that helps another and vice versa. This can happen with NK cells, which are innate immune cells that are nonspecific. However, when they encounter pathogens by innate mechanisms, they can also produce interferon gamma. And in return, the macrophage will produce a cytokine known as IL-12. IL-12 will actually activate the NK cell. Will also, in this case, if the macrophage was able to produce IL-12 toward the TH cell, the TH cell would take it and would make the Th1 CD4 positive T cell a better Th1 CD4 positive T cell. So IL-12 can work in both the innate and the adaptive immune response. Lastly, we have endocrine. We've already talked a lot about endocrine, and you should be familiar with its effects. The endocrine method is how all of our acute phase cytokines work. IL-1 beta and TNF-alpha are going to the hypothalamus to induce fever. IL-6, produced by macrophages, goes to the liver to create acute phase reactants like C-reactive protein and mannose-binding lectin. Both of these bind either to phosphocholine or mannose on the surface of bacteria and act as opsonins, helping to mediate phagocytosis of the bacteria and initiating the complement cascade, which is an innate response defense mechanism that we'll cover in a future video. TNF-alpha and IL-6 can increase your fat and muscle metabolism, which not only induces fever, but also, when taken to an extreme, can cause wasting and pain, a process known as cachexia, which is often experienced by cancer patients. Lastly, they can travel to the bone marrow and the endothelium to cause neutrophil mobilizations. Your neutrophils aren't allowed to just go anywhere because they're really potent killers, but when they are mobilized and brought to the site of inflammation, they result in phagocytosis. So, in summary, we have 3 ways of using cytokines: autocrine, paracrine, and endocrine. Where the cytokine travels and how short a distance to have an effect is really how these 3 terms are used. So autocrine is the cell that makes it, is the cell that uses it. Paracrine is short distance but a different cell, and endocrine is long distance. Our examples included IL-2 for autocrine, interferon gamma and IL-12 for paracrine, and our acute phase reactants for endocrine.